This is a talk that we've been promising for about a year now. And this came out of a peer-to-peer learning initiative that we had last year, where we explored property-based testing in a variety of languages, JavaScript, Scala, Python, what have you. And so after 1 year, we've been preparing this for a long time.
Just setting the expectations at the right level.
Yeah, we've been preparing this. Just make sure that this is the... We haven't been doing this morning. We've been doing this all year. And we'd like to share with you what we learned and give you a proper introduction to property-based testing. So first of all, what do we test? What do we test our code? You're the experts. Yeah.
No idea.
No idea.
Make sure it works.
Make sure it works.
Make sure it breaks.
Make sure it breaks. That's it.
Well,
That's a good point.
So there's a number of reasons: documentation, quality assurance, preventing regressions, and of course as a design aid when we do test-driven development.
what's that?
Well, I don't know. So how do we test? What tools do we have?
We do design scenarios of failure.
So we can have compilers telling us if the code we have is breaking. It's great with typed languages like TypeScript or Scala. We have automated linting, static code analysis, just a bunch of patterns that can be checked automatically. It's pretty easy to set up, and you get some return out of it. It's not real testing the way we like it, but it's something. There's manual testing.
Yay.
And there's automated testing as unit testing or behavior-driven development. And within automated testing, we have example-based testing, which is what we normally use, and the focus of this talk, which is generative testing. So example-based testing is great, but there are a few downsides to it. Can you think of any limitations that you've run into?
You don't know all the cases. You can't do all the cases. You can't imagine all the cases.
Yeah, you can't really get all the coverage that you want, and you have to think, no, which cases are significant? How much coverage is enough? How many tests do I have to write to get the level of confidence that we expect? And after you write a bunch of tests, how many of those are actually relevant? And how much work would it take to change them if the requirements change? That's why property-based testing exists. So, Miguel.
Okay, so the rationale is instead of writing specific tests, we can use a framework that will, based on different sets of properties that we can define on the system under test, automatically generate possible values. So, and how does this work? So, the most important concept is the concept of generators. So, what is a generator? A generator is something that will generate possible values automatically based whenever you want. And based on that generators, you can then assert on properties. Well, let's think of a simple example, say sorting a list. Can you think about a couple of properties on sorting a list? What is a property like after the list has been sorted? Couple.
Every 2 elements must be sorted.
Yes.
Length should be the same.
Length should be the same. Good. And I think that's about it, right? So, pretty much all property-based testing frameworks provide already a lot of generators built in. You don't have to code anything to use them for numbers, strings, lists, tuples, whatever. Fixed ranges of numbers. And then you can extend them, but we'll look at it later. Yeah. So
let's look at a simple example of addition. So you've probably remembered this from your math classes, and if you don't, no shame on you. So how do you convert this to code? So we have an add function, and I already wrote a couple of. I've commented the rest, but I've added a couple of tests. We're using JSVerify, which is a property-based testing framework for JavaScript and TypeScript. And we're going to use the integer generator that comes out of the box from JSVerify. So we have the function we want to test, and we have a couple of properties that are probably familiar to you. There are two ways to write this test, by the way. So there's a check for all, which is using the functions that are provided by JSVerify. But there's a shorthand if you use something like Jasmine or Mocha or Jest. If you have a init function, a global int function, you can use the property shorthand, and that makes tests nicer to look at. So we're going to forget this for a while and use just property. So we have a couple of properties in place. So there's commutativity. A plus B is the same as B plus A, and it should hold. And we have all the tests passing right now. And there's associativity. A plus B plus C, doesn't matter what order you add them in, it should always be the same. And there's identity. So if you add, let me uncomment this, if you add 0 to A, it should give you the same value, right? Oh, but we have a test failing because we have a bug in our code. We were actually doing multiplication, which also has commutative and associativity. So if we fix the code, it should hold for identity. So properties are great because we had this bunch of possible values that we're testing, but it still failed because we were implementing the wrong function. There was a bug in there that probably wouldn't be caught if we didn't use the right tests. There's a bunch of other properties that we can test. They're more or less, they're not the primary properties of addition, but we can test these as well. There's a successor. Any number plus 1 is always greater than the number that we're adding to. And again, it passes. And there's opposites. So any number plus its negative should be 0, which is basically the same as identity. And once you mix it in with actual multiplication, there's something called multiplicative distributivity. And it should also hold true because A times B plus C should be A times B plus A times C. So we have, because we're generating these numbers, we're not testing for specific instances. We're not testing 1 plus 1 or 2 plus 2. And this is a really simple function. But if we add a more complex function with several inflection points and so on, it would be trickier to find a sufficient number of values that would sufficiently cover this function with tests. And having this framework generate numbers, and by default, these frameworks usually generate 100 numbers per test. So what we're actually running here in 7 tests is 700 tests, really, that are running behind the scenes.
You can set the number of numbers that
you can set the numbers, because there's of course you're running the same test 100 times. It's going to have a performance overhead on your tests. You want them to stay fast. And if you're generating stuff like booleans, it doesn't make sense to generate 100 booleans because there's only 2 possible values.
Well, it's JavaScript we're talking about, so there's actually a couple more.
So, okay, this is the really basic stuff of property-based testing. You generate a value, you fit it as an input to your functions, and because you're testing something that's so generic, you can't really re-implement stuff. You have to look behind the expected value that you usually test against. So in regular instance-based testing, you You have a couple of inputs and you expect an output out of it, and you compare the two. But because we have generated inputs, getting to the expected output is trickier. So you have to think in more, in higher level, on a higher level. So it does require some changes in the way you think. So this is the code we just did. So yeah. Okay, so we've looked at addition, which is a really simple case, but when we're talking about the code we write, sometimes it might not be clear what kinds of properties we can find. So let's look at a couple of examples. In our code, we can have several ways of achieving the same result. So while we can set the property, if we do one thing, then we do the other, we should have exactly the same outcome if we do the actions separately. So that's one property. Round trip tests, where you can transform one thing into another. Say, for example, typical case, you're writing a controller, you need to be able to parse the JSON, and you also might need to be able to generate the JSON. So your parsing and parsing function, so if the parse of the two JSON function should be the same as the original JSON, for example. That's something you can write. Invariants, so in the beginning we've said the list example, but there are things that should never change on our domain, regardless of what happens. For example, if we sort the list must have the same elements. They must be in order. The size is the same. When you're mapping over a collection, the mapped collection should have exactly the same number of elements.
And the same elements too.
And it's, well, not you might be transforming, right? Right. If you're transforming over a list, might be something different. So whatever invariants you can think on your system, you probably could test with a property. Right? Length is usually the easy one. Yeah. But it might be, say, for example, let's talk about, let's say, financial transactions. Regardless of the order of debits or credits that you do, for example, on a system, then the balance should be, for example, always positive. Right? So you're implementing a wallet. So regardless of the order that you do things, it's always above 0. Idempotence, which is you can do the same operation over and over, and it should always achieve the same result. You can also use property-based testing when you have like two alternatives of achieving the same thing, and you want to compare them, or maybe to double check them. So you can have like you're implementing an algorithm. Let's say a new. You've reinvented sorting, and you've managed to beat quicksort, and you believe that you did. So you want to make sure that you're actually running it better, so you can use property-based testing for that. Yeah, you generate any number of a list of any number of elements when you compare the outputs, and if they're the same, great. And you can even have a property if you're really confident that the execution time of your function is faster than the legacy one.
A really interesting use case for property-based testing is we've been talking about really simple cases where we're unit testing a function, but you can think of it as testing the system border through the system interfaces. So if you have a legacy implementation that you're trying to refactor, you can use property-based testing based on interactions that you do with the system and making sure that you have exactly the same results. So that's one of the hard things, which is to migrate from legacy systems to a new system, making sure that they behave the same way and correctly. Let's now look at our favorite.
Our favorite coding exercise, yeah.
Okay.
How would we do FIZZBUZZ?
You want me to?
If we had to use property-based testing, so I already set up. There's a FIZZBUZZ here, but I'm going to break it. Sorry. Okay. going to break this. Now, what would be a good property to test with FIZZBUZZ?
Sorry. Can you repeat that, please?
What would be a good property to test for FIZZBUZZ?
Every multiple of 3 returns 3. No.
We can start with that. It's not exact because 15 should
Yeah,
return
15 will
fizz.
fail.
But yeah, but let's start with that. So we'll generate an integer,
Multiplied by 2.
and we're going to do a very simple test. We're going to do FIZZBUZZ I plus 1. I'm using the range function from Lodash, hence the plus 1. And we should know that the first element should be a fizz. Now, this of course isn't true. Multiples of 3 are fizz. Start with fizz, actually. So we can do something like starts with fizz. Right?
No.
So it fails because, well, not all of these numbers are multiples of 3.
Does he say what is the number that failed?
So this is where custom generators come in. And what I talk about those?
Yeah. So the beauty of property-based testing is based on the primitive generators that are already available. You can compose new ones. For example, you can have an email generator that you can grab the primitive string generator that will generate random strings, and then you append a domain to it, and then you have a valid email generator. Or you can have, let's say, generate objects, not only just a simple string, right? So you can have generate a person generator, where you can have, you will reuse the generators for, let's say, the first and the last name, an age for an integer generator for age, and then you can reuse another generator that you've already defined previously. Should we move on to the code example?
So whenever you're creating a custom generator, you have to think about shrinkers. And I'm going to show you an example of what a shrinker is. Shrinker is a function that will go over the generated values and try to find the simplest value that still fails the test. And so shrinkers are useful only for when test fails, right? And here's an example. So I have something here that compares a couple of shrinkers. So we have a custom generator here that uses a shrinker. So this custom generator, what it does is it takes a number and it generates an array of up to those elements. It can be any value between, I'm going to use here 100 because that's the value I'm passing it here. So it's going to generate any numeric array between 0 and 100 elements. It's got a generator function and it's got a shrinker function. The shrink function it should be a right inverse of the first one. So that means that when you apply the generator function to the shrunken value, you should get the original value. This is a requirement, otherwise it won't work. It'll blow the call stack. And you can sort of cheat and provide a generator that doesn't shrink anything, and that's for that you use the blast function that JSVerify provides, and you just give it a generator function. So what this does is it creates an array, and the right inverse of this is you count the number of elements in that array, and you get the original value back. What does this mean in practice is that I've created a count function that introduces a bug that only counts up to 2 and then returns infinity. And this is an intentional bug, of course. And when I run those tests, the version with the shrinker gives you the smallest array that fails the test, in which case it's an array of 3 elements. Whereas the other one gives you, the first array that actually failed, and it's one with 15 elements. 16. And every time you run this, the version without the shrinker, it gives you, any number of elements. And this is really hard to debug if you are getting this in the output. If it's a really big generated object that's failing the test, so it complicates reading the test output. It's not consistent because every time you run the test, it gives you something different. Whereas the first one actually gives you a very good idea of what's actually failing. So if you go in here and say, okay, this is not what it should be. So I'm just going to fix the code, and it's passing. Okay, let's go back to FIZZBUZZ.
Sure. Before, if you notice, whenever it fails, oops.
Sorry.
Okay, it's slightly. Okay. You have this an RNG stat, which is basically the random seed that was used for this particular run. So if you're trying to debug a particular case and you want to make sure that you're going to hit that particular example, we can force the random number generator seed to make sure that the test is repeatable. Okay.
So okay, we have a generator here for numbers, and it's failing the fizz test because we haven't implemented it yet, of course. And it says counter example 0. That means that the first thing it actually tries is 0, and it reduces, or if it doesn't, it reduces down to 0. And because 0 is a multiple of 3, and it doesn't find one, we'll just implement a cheat test and say, okay, this is fizz. And now it says, okay, 1 is failing, but 1 isn't a multiple of 3, so we have to actually fix our generator first. So in order to create a generator like we did here, I'm going to reuse this, or not. So it's a multiple of 3, it's an integer, and we smap this. So the multiple of 3 is simply I times 3, and we have to provide the right inverse, which is the number divided by 3. So instead of integer, we're going to say it's a multiple of 3. And now the test says, okay, the counterexample is 3. It's filling for 3, so let's do it properly now. And it's not passing. Why? Starts with fizz. Oh, sorry. Okay, good. So we can do the same thing for multiples of 5. So we can copy and paste this more or less. And it should end with buzz. So same thing, multiple 5. No, multiples of 5 start with fizz. Oh, sorry. And with buzz. That's the one that's failing. Okay, let's do it. No, it fails because there's a multiple of 3 that doesn't start with fizz. So that's the test for FIZZBUZZ. That's actually good. Okay, this isn't foolproof. This says for a wide variety of tests, but it's not 100% correct because you can introduce junk in the middle of the test and still fail. you can have a property that says that the elements of the resulting array are either FIZZBUZZ, or a number that will catch this sort of garbage in the middle. So, for instance, you can say that sorry.
So it should be one of
Expected outputs, whatever. You still give it an integer. We're still testing just one number. And it's FIZZBUZZ. Outputs 1, 0, and it should be either the number we provided it, as a string. It should be fizz, buzz, or FIZZBUZZ. So it contains, includes, index of, should be greater or equal than 0. I think I mixed it up.
No, it's an extra parameter.
so we'll have the brackets.
Okay. So for every integer, and it's actually true, we're not
We're not messing with
with the
the results.
results.
but
We can try now, and it'll break for 0. And if we do it for 3, it'll break for 3. And this is the smallest possible value that fails. So it's really helpful. And again, for 5. So this is one test. And the other property we can test is the length. We know that the resulting range is the same length as the range that you provided. So length. Actually, I have this test already written out below. Well, I don't. I have the element sequence, which is also interesting. So the thing is that if you break down the range that you created, each element should be correct. So you compare what we're actually doing here is that the whole FIZZBUZZ range is the same thing as a map over each individual FIZZBUZZ element that we have. And this tests for stuff like order, because you can reverse the list. It would still pass a lot of the tests, and you don't want that. So back to the slides. So this is another example of the shrink function, and we use it to generate an arbitrary date time using smap. Let me just silence this FIZZBUZZ test here. So we're generating a date time with and without a shrink function, and again you get the same, the smallest possible date versus some date. That doesn't particularly mean anything. There's something else that JSVerify allows you to set, and that's the show function. And that's just something for output, so you can predefine the output. This is the default that's given, and it's a JSON encoded date, and this is the string from JavaScript. You can use isostring, for instance. It'll give you a different format. And yeah, back to the slides.
Okay, another concept which is tightly related with generators and composing generators is that you can composing generators based on numbers, as I said, very straightforward. We've already seen that, but you can also use such that to, based on an already existing generator. For example, this is the arbitrary user generator that we've used before. Well, I just want minors. So, and now we have a minor generators because we've applied the restriction on the age. So it will generate all sorts of users, but we can be sure that the age will be always under 18 for this particular one.
So on the prepared example that we have for FIZZBUZZ, there's actually a such as that limits this. And we've created a couple of helper functions. One gives you the multiple generator, and it's the SMAP that you've seen. And this is indivisible, and this acts like a filter. So what we do here is that, let me break the line here. We call such that the number is not divisible by the number that you've given it. And now you can test fizz and buzz and FIZZBUZZ in isolation because we're giving it a generator that's a multiple of 3 but not a multiple of 5. That's a multiple of 5 but not a multiple of 3. And for the rest of the numbers, that's not a multiple of either 3 or 5. So there are two different ways to approach this. I went off script on the example above, and it's still valid. There's still valid properties like these ones. There are different ways to achieve the same ends. And yeah. So where can you use this? Well,
Yeah, there's pretty much one available for.
Yeah, there's pretty much one available for every language. Some language have not as great support for generators. So for instance, JSVerify doesn't allow you to do complex stuff like commands or there's the concept of commands that you can have on a quick check or scala check. And that's basically if you have a whole system, you can create a generator that generates a series of commands, and each command is associated with an expected end state. So basically you have a big system and you say, okay, let's suppose that our commands are log in and log out. After a series of logging in and logging out, any series, you should have an expected state. You're either logged in or logged out, right? And this is something that certain languages offer. Unfortunately, some are still lagging behind. But
Quick check was the original.
Quick check was the original, library for this. And scala check, it's pretty close to quick check. It copies a lot of stuff from the original API. I don't know about the others. I haven't looked at them all. But JSVerify also takes some inspiration from quick check, although it's inherited from an older library called JSCheck that was started by who's the JavaScript dude? Douglas Crockford. It was started by Crockford, but he sort of abandoned it, and the JSVerify guys picked it up, which is why the imported model is called JSC and not JSV. Anyway, yep, so pretty good support. And the thing is, you can use this combined with your tests. So this improves coverage because you can generate any number of inputs. And it's not meant to replace example-based tests. Not only because it's harder to get 100% coverage using property-based testing, but also because there's a performance impact on this. If you're running 100 tests for every test that you used to have as an example-based. So it's not meant to be a full replacement. It does require changing how you think about tests, but there are a few easy to follow patterns that you can look into, like the examples that we've mentioned before, idempotents and invariants, the getters and setters, and any operation that's reversible you can basically use to test. So, any questions? Okay. Thank you.